Hey everyone, in this video we're going to talk about gears in general and specifically interference in gear trains. And this video is part of a lecture series on mechanical design 2, and it's the third lecture of this series. So to start with, we want to talk a little bit about interference, and there are some notes that are already written here so that we can save a little bit of time, but essentially interference means if there is contact of portions of tooth profiles that are not conjugate. And this is usually due to poor design or improper mounting. So we've talked about conjugate design in previous lectures within the series. And if we look at the diagram below that comes from a textbook that we have on gear trains, we can see that typically a gear would be initially designed as an involute profile, and then we would have a cut at the top and then another involute profile. And if we have this involute profile, what happens is if the design is not made correctly, or if there's improper mounting, or a certain way that the gears are too big to mesh with each other, what can happen is we have this phenomenon called interference, which we can see right here. And the interference is when essentially a gear, if we had another involute profile here, we would have the involute profile showing up like this, and we can see that there would be a crash between the gears and a problem between the gears. And this is something that can happen, but can be prevented pretty easily because it's something that we know could happen, and it comes from geometry mostly, and sometimes improper mounting. So most of the time it can be prevented by having the right design, but also making sure that the mounting is correct. If I erase this part here, you can see that there are ways in which we can kind of solve this problem of interference. Now, one way to solve this problem is to say, let's modify the tooth profile under the base circle of the pinion, and let's modify it so that essentially under this base circle of the pinion, we actually make it not an involute profile. So what we can do is we can undercut, so it's noted here on the left side, we have undercutting. We can undercut this piece so that it gets cut up so that it fits the gear above. So let's look at some ways in which we can solve this problem. So we already talked about one. So one way is to undercut. And the real problem with undercutting is that it is a good solution, and it's definitely something that can be done. The problem is that we usually weaken the tooth. And I'll put weakened teeth in general because you would have to undercut every tooth basically. So this problem of undercutting is that essentially we weaken the tooth. It can be done as a solution, but better than that, we can do some other things that can be done. So another thing that could be done, which is something that can be done in design as well, is lowering the addendum. And what we mean by lowering the addendum is essentially cutting off or cutting the tooth at a lower level than it currently is. And this, if we do it, for example, here, we would see that we would get rid of the interference if we cut the tooth. Now, the problem with that is that the force transfer would happen on a shorter distance. Therefore, there would be more force or more pressure on each tooth to make the solution happen. So that's another thing. Now, the other solution is to take the same design, and instead of having the number of teeth that we currently have, you could add more teeth. If you add more teeth, you're able to add more smaller teeth and distribute the load more, and this can be a very good solution. So what the American Gear Manufacturers Association did is they decided, let's come up with a way to make sure that we prevent interference in terms of number of teeth. So we don't have to do these other two solutions, which are more like after the fact solutions. So the real solution here is to always think of trying to make a minimum number of teeth so that we for sure, if we use an involute profile, we will not have a problem with interference. And there's a lot more involved in this as well, but this is kind of like a design constraint that we have to add to our system. And the equation for this is n sub p is equal to 2k over 1 plus 2 m sub g times sine squared phi, all multiplied by m sub g plus the square root of m sub g squared plus 1 plus 2 mg times sine squared of phi. So 3 things that we need to know from this. So we need to know what mg means or m sub g means. We also need to know what k means, what phi means, and so we already have defined phi, but I'll redefine it really quickly. It's the line of action angle, or the pressure line angle. Typically, this is 14.5, 20, or 25, as previously mentioned. M sub g is called the gear ratio. And not to be confused with M, which is the module. M sub g is the gear ratio. So M sub g can be defined as ng over np. Okay, and by this, what we're finding out with this equation is the term above here on the left. We're finding out what is the number of teeth that the pinion needs in order to not have interference. So it's a condition for interference. And again, I will show you a little bit later in this lecture that we do have a formula sheet that you can look at that's been created by me for you to help you in whatever problems you have in the future. This formula sheet includes this formula, so you don't necessarily need to copy it down from here. You will have a version of the formula as well. So that's that, and then K is a term to define whether, so K is equal to 1 or 0.8, and K is a correction factor for whether if we have full depth teeth or what we call stub teeth, which would be teeth that are cut off. Okay, and following that, if we did a simulation of these and said, for example, we have a gear ratio of 4, which means that, for example, it would mean that the number of teeth on the gear is 4 times more than the number of teeth on the pinion. We have a contact angle of 20 degrees, and K is equal to 1. We would get that the number of teeth in the pinion to not have interference would be equal to 15.4. So because it's equal to 15.4, we need to go higher than that. So we need to say we need at least 16 teeth. We can't go to 15 teeth and round down. We always have to round up. So that would mean that our system, if we wanted to avoid interference, would need an NP of 16 teeth. And I'll put T for teeth. And that would mean that the number of teeth in the gear would actually be 4 times that, which would be 64 teeth. Okay, and that's pretty much it in terms of what we want to learn about interference. Now we're going to have to check for interference whenever we do problems. If we're below the value for interference, then we have to change our numbers, especially when we're starting to do designs. When we do problems in your book, and if you do a problem with a very, very defined answer, and it doesn't ask you to check for interference, you don't always have to check for it. But it's always a good habit to always check for interference before you even start the problem, or once you have your teeth number, to make sure that, let's say you designed a gear train with a number of teeth on the pinion of 12, you would have to double check that you wouldn't have interference based on the gear set that you have. And obviously the number changes with the m sub g term, the phi term, as well as the k term. Okay, so then now we're going to move on to introducing gear trains. And what gear trains are essentially a, so I'll put here gear trains. So gear trains are just successions of gears put together as a system. So instead of just having two gears together, a gear train would be at least two gears together. So more than two or two gears together. And we need to try and start understanding what's happening from that side. Now, some of the equations that we can recall from previously and that we're going to add a little bit onto based on diametral pitch or module, depending if we use US units or SI units, is if we remember we had omega 1 over omega 2 is equal to R2 over R1 is equal to D2 over D1, and it's also equal to N2 over N1. So the ratio between the number of teeth and the diameters is also going to be equal. So this is a new thing. And we're going to talk about why this new thing is important. So if we look at, so I'll put module slash diametral pitch so that we talk about both things. But if we think about module and diametral pitch, then this module and diametral pitch has to be the same for both gears. And this is both gears that are meshing. So if you have two gears meshing, so let's say we have two gears meshing, and let's say we have 16 teeth and 48 teeth, just like in our example above, then it means that the diametral pitch should be the same. The reason why, or the module. So remember, module is D over N, and diametral pitch is N over D. So the reason why we need this and the reason why this has to happen is because if the module is the same or the diametral pitch is the same, what we're saying is that there's the same number of teeth per inch of gear or inch of distance. And if there's the same number of teeth per inch of distance, that means the teeth are going to essentially mesh together. So if I actually zoom into the side of the gears, so let's say I look at a zoom in of the side of the gears together, if they have the same diametral pitch, they would have the same spacing between the gears, and that would mean that the gears would mesh in together. So I'm drawing the gears as just sticks, but the sticks would essentially mesh together very, very well. If we don't have the same diametral pitch, what would happen is if you have double the amount of teeth per diameter, for example, on the gear, what would happen is you would have extra teeth like this, and they would never mesh with the other gear. So in order for two gears to mesh, we need to satisfy this requirement of diametral pitch being the same between both gears and meshing. And therefore, it means that if we have the equation, if we say that d2, sorry, not d squared, but d2 over d1 is equal to, we can rearrange the diametral pitch equation essentially to say this is equal to n2 over p, and then this is equal to n1 over p, and since p is the same, we can cancel the p's out, and we're left with n2 over n1 as previously stated. So that helps us a little bit in the analysis of our problem. Now, if we look, so I'm going to show you the formula sheet for module 1, and this is chapter 13 formula sheet in reference with your book. So you have a lot of units on the left side explaining all the units for the different things. Again, this is a formula sheet that might have extra information that you might not need all the information, but it's there for your information, and it's there for you to edit and for you to play around with and add stuff to it. So we can see on this formula sheet some of the stuff that we've already looked at. So you can see this R1 omega 1 equals R2 omega 2. Then we have this equation right here, which we wrote at the start of here. And then we have other equations determining some of the other changes. Some of the other things that we have here, we have the equation with the mg, which we just wrote out. So if you want to use that equation, you're more than welcome to. And then there's some other equations here that will be looked at later on in the chapter. So based on this formula sheet, you can always refer back to it when you're doing problems or when you're doing anything. I might look at it as well when I'm doing some extra problems as well throughout the lectures. So going back to our lecture itself. So let's look at what a gear train is, and let's draw a gear train from scratch. So one way to teach this is to say, okay, here's a gear train, try to design it and try to work with it and try to figure out the velocity of gear 6 or velocity of gear 7. Now, what I like to do is to draw it from scratch, and it's going to be a little bit of a sketch, but it's going to be helpful in terms of understanding what's happening and how we actually draw these systems from the front view and then from a top view as well. So let's draw a system from front view of a gear set. So let's say we look at a gear set. So what we're going to do is I'm going to draw some gears together, and then we're going to kind of analyze the system as we go. So we have one gear, then another gear that is bigger, okay, and we can move it slightly down. So let me just redraw it so that we have it slightly down. Okay, then we have another gear here that's going to connect with this one. And then this gear is also going to have a gear that is going to be shown in the background of it. So we're going to have kind of a shaded gear in the background, and this is the convention on how to draw it. And we'll talk about what that actually means once we draw the system. And then we have another gear that is meshed to this gear that is in the second level essentially. And now we can draw all the centers of these gears. So we have these centers where the axles are. Now, by convention, and this is how gear designers draw this essentially, by convention, they don't start with a gear number 2. They actually start, number 1. They start with gear number 2. So the first gear on the left side is sometimes a pinion, sometimes a gear, it depends. Usually it's a pinion, but it depends. Is going to be called number 2. Then this would be number 3. This would be number 4. Then this would be number 5, which is on the same axis as number 4, but is side by side essentially. And then number 6. So we have this design. Now, where is the number 1? So number 1 is actually called the frame of reference. So what they do is they design kind of like a control volume in fluid mechanics. They call this the frame of reference because sometimes you're going to be faced with gearbox designs or gear designs with rotating frames, such as a planetary gear set or something like that. So this is the front view of a gear system as is. Okay, now if we wanted to draw this from the side view or from the top view, we now have to see what's happening from the top view. So from the top, what we're actually seeing is something like this. So we have gear number 2 with an axle in the middle. Okay, that axle is held by whatever way it is, but it's held by something somewhere. Then we have a gear number 3 that's also held by an axle in the middle. Okay, and these axles are shown here. Typically, the axles have names of A, B, C, and D, lowercase. Okay, so each one would have A, B, so this would be gear 3. Then gear 4 would be connected to gear 3. And gear 4 is going to have an axle that goes through it, and that also connects to gear 5, which is bigger. Okay, so this is gear 4, gear 5, and this is axle C. and then gear 5 is finally connected to gear 6 with its own axle right here. So we see that we've been able to design the system on the right side of this diagram. Essentially, we're redesigning the system, but from the top view now. So this is pretty much what we would see from the top if we were to look at the system. Okay, and we can extend shaft C all the way to 5. And so we can see how we have to use a depth to understand the system a little bit and understand how the system is working in itself. Now, we could also say that we know that, for example, gear 2 or pinion 2 is rotating clockwise, and then we can start putting into the system in what direction every gear is rotating. So gear 3 would be rotating counterclockwise, then gear 4 would be rotating clockwise, which means that gear 5, you have to be careful with this, gear 5 is also going to be rotating clockwise. Okay, so they're both rotating clockwise because they're both on the same axle. And then gear 6 would be rotating counterclockwise. So we would essentially have a motion that goes from clockwise to counterclockwise. And what we might be asked in this type of problem is, for example, we would be given some information and we could be told to find the speed of gear 6. Okay, so we're supposed to find the speed of gear 6. Now, speed doesn't mean miles per hour. In this case, it means angular velocity. So we've already figured out the direction of the speed. So by analyzing the diagram and looking at the diagram, we were able to state that the direction of the speed is counterclockwise. Okay, so that's one thing first. The other thing is we're going to be using two different terms for speed, and so far we've written our equations in terms of omega, which is angular velocity, but we're actually going to use a lowercase n for angular velocity, which is what is used more in the book itself and in convention as well. The difference between the two is that omega is usually given, and I'll switch back to black color. So omega is usually given in radians per second, and lowercase n is given in RPM. Okay, so lowercase n is essentially exactly the same as omega. It's just different units of measure. Okay, and so whenever we're looking for the speed of gear 6, we're either looking for n sub 6 or omega sub 6, depending on the unit that you're looking for. Now, typically, if your problem is given in RPM, we try and keep everything in RPM. If your thing is given in angular velocity in radians per second, you can keep it in radians per second. And if you switch between the notation, it's not a huge problem for me. Just keep in mind that there is a different notation for different things. Okay, so going from here, we need to find N6 or omega 6. Let's go with N because it's easier RPM for now. So what we can write is we can write our governing equation. Okay, so we have the two first gears. So let's look at two first gears. For the two first gears, we can say that omega 2 over omega 3, which is the two first gears, right? Because we start with number 2, is equal to N3 over N2. So let's say we know the number of teeth. So each gear has a certain number of teeth, N3, N4, N5, N6, or we might know all the diameters, which we could use the diameters as well, or we know all the radiuses. Now, what I'm going to write here is I'm going to write that this is also equal to N2 over N3, okay, which is essentially the equivalent of omega 2 over omega 3. So I'm going to use this side of the equation moving forward, just for this type of problem, and I'm going to say, well, I need to be given something in my problem as an input. So usually N2 will be given because that's the input from a motor or something like that. So let's say we're given N2. So I'll write that N2 is given in my problem. Okay, and the idea is to find N sub 6. Okay, so we're given N2, and we know the number of teeth of each gear because we can count them visually. So what we can do is we can rearrange that equation on the left and say that N sub 3 is equal to negative N sub 2 times N2 over N3. Now, where does the negative come from? The negative comes from the fact that we're changing direction. So if N2 is a positive number and we assume that clockwise is positive, N3 has to be negative because it's going to be rotating in the other direction. Okay, so here we have to take into account the direction of things, which we haven't up to so far. So then what we can do is, so we're going to say that we made an assumption that clockwise is positive, therefore N3 is going to be negative, and we made that assumption. Now, from there, we can then say, well, we can write a similar equation between N4 and N3. N4 and N3 are, or lowercase n4 and N3 are related together. So we can write an equation that says N4 is equal to minus N3 times N3 over N4. Okay, so same as before, we just rearrange the equation so that we essentially get N4 isolated as a function of N3 and everything else. And so we can see how little by little we could, if we wanted to, we could bring this in to here and bring in the minus N2 equation and multiply everything together. Now, moving forward, N5 is, so you have to be careful here, N5 is on the same axle as N4. So it's going to be rotating at the same angular velocity. So N5 in this case is not connected by gear teeth. It's connected by an axle. So it's going to be going exactly the same velocity and in exactly the same direction. So it's going to be going clockwise as well. So essentially, N5 is going to be equal to N4. And then N6 is connected by gear teeth again. So now we have N6 is equal to minus N5 times N5 over N6. Okay, so we have this whole equation. Now, if we substitute everything into the equation and we take the N6 equation, plug in N5, which means we plug in N4 and N3 into all the equations, we essentially get that N6 would be equal to negative minus N2 over N3 times N3 over N4 times N5 over N6, all multiplied by lowercase n2, or the angular velocity 2. And we know that N6 is negative of all that multiplied by N2, because we know, if we look at our problem, we know that N6 is going counterclockwise, so it should be the negative of N2. Okay, so then we can simplify the equation a little bit. We can say, all right, well, we have two redundant N3s, so we can cancel the N3s, and we can simplify our equation to say N6 is equal to negative N2 over N4, and then we'll group together N5 over N6, we'll keep them together, all multiplied by N2. Okay, now we can write this in a slightly simpler way and actually take a shortcut. So one way to solve these problems is to always do this process that we just did right now. So write the equation for every gear connected with each other and then come up with an equation for it. Now there is a shortcut, and this shortcut is to write the following equation. N last is equal to E times N first. And this equation is also in your formula sheet, so you can use it in your formula sheet. And this E term is called the train value. So it's a value for the train that essentially represents all the reduction in speed or the increase in speed that we have. Now, obviously, one thing we have to take into account is that E is going to be positive if the last train is rotating in the same direction as the first gear, and is going to be negative if the last gear is rotating in a different direction or opposite direction than the first gear. So I'll write it down here as a rule. So this is if rotating in opposite direction, so last to first, which is the case in our problem right now. So if rotating in opposite direction, we have a negative. We need to add a negative to our equation, okay? If not, if it's rotating in the same direction, the train value is positive and then we're good to go. So what does the train value stand for? So one way to think about the train value is to say that the train value is equal to the product of driving tooth numbers. And divided by the product of driven tooth numbers. So we know that the gear teeth of 2 are driving essentially the whole system, right? So if we go back to our drawing, we can see that number 2 is driving number 3, and number 3 is driving number 4. Then number 4 is not driving number 5 because they're on the same page, they're on the same axis. And then number 5 is driving number 6. So let's figure out the ones that are driving on top. So the ones that are driving are the following gears. So we have E would be equal to N2 times N3. So N3 is a little bit of a special one. It's an idler. And whenever you have an idler, it's driven and driving. So it's driven by 2, but it's driving 4. It's between 2 gears, essentially. So it's there to change the direction, usually. And so that one is actually driven and driving. So it is driving 4. And then 4 is not driving 5. So 4 doesn't drive anything. It's just driven. And then 5 drives 6. So we'll add N5 to the top. Now, the ones that are driven, 2 is not driven because it's not pushed by anything else. It's pushed by a motor or something on the axle, but it's not actually pushed by teeth. So N3 is driven by N2, so we have to add it. N4 is driven by N3, so we have to add it. And N6 is driven by N5, so we have to add it. And once again, because we have an idler, the idler gets driven and driving, so we cancel the N3, just like we did before in our problem. So then what we can say is N6, which is our N last, is equal to E times N first, which is N2. And the one thing we need to add is our negative in front of there because this is clockwise and this is counterclockwise. Sorry, the opposite way. This is counterclockwise and this is clockwise. Okay, so that's how we would solve a little bit faster the problem. Then the only thing we need to know is N2, N4, N5, N6, and then we can solve the problem by dividing them by each other and you get your rotational speed of 6. So there, you will have some study problems and you will have some work to do in terms of those values to be able to solve for that. So this is the conclusion of this lecture. In the next lecture, we're going to start with an actual example of this and figure out how we can do a problem of a gear train in terms of applying this type of analysis, including interference as well. And then we'll talk a little bit more about speed reducers as well as specific cases of compound reverted gear trains. So we'll see you in the next video for that.